My channel STEM Cafe, where we treat everything science, technology, engineering, and mathematics. This time around, we are going to treat some questions deeply to demonstrate the way to work them out. You don't want to assume anything, so that after watching this, you won't have any challenge in handling anything about relative velocities and combined velocities, especially two dimension. So please, I need your attention. And before we go on, I'd like to remind you, if you have not subscribed, to subscribe and watch other videos that we have done. Share and comment, please. I would like your comments and advice on how to improve. All I'm doing is for you, and I'm here mainly because of you. Thank you as you do that. Let's treat this first. A sailor is sailing on a course 0-10 degrees at speed 30 kilometers per hour. Ship B is sailing on a course 340 degrees at 20 kilometers per hour. At a certain time, B is 40 kilometers from A on a bearing 060 degrees. After what time will they be closest together, and what will be their minimum distance apart? The first thing is to represent the question diagrammatically like this. You are told that one of the ship is moving 10 degrees, 30 kilometers per hour. He saw another ship 40 kilometers away, moving 340 degrees at 20 kilometers per hour. And we are asked now to find the time they come closest together and that distance apart. So the first step is to do this. Then work out the relative velocity. If you are using diagram, construction like in bearing and locus. So the first step, 1, calculate the relative velocity. And direction. So here I will explain if you are working it or you are drawing. Now look at this. You would have drawn this using your protractor. You get the angle 10 degrees here, 60 degrees here. You draw straight line using your ruler and whatever, set square. From here too, you'll be able to get your 20 degrees. Just showing you what to do. After that, we now get our relative velocity. You can use calculation or you can use drawing. If you want to use drawing, you draw. Let's say, okay, I want to calculate, let's call this one B, and this one is A. The relative velocity of B to A, that is VB minus VA. This is what you do. What direction is this one going? This is it. You draw this 20 degrees, and you use your measurement. You draw to scale. This one will denote 20 kilometers per hour. Here too, from here, remember from addition of vectors, we have 30 kilometers per hour here. It was going like this normally, and we have 10 degrees. So you draw 30 degrees down like this. 30. So you have 10 here, by vertically opposite angles. And this one alternate angles, you have 20. So you have 30 degrees here. So this will be the BVA. That is the relative velocity of B to A. So in your diagram now, since you have drawn this, you measure this place. It will give you a value, and you get this angle using your protractor. You get that angle using your protractor. The first step is to get your relative velocity. Now let's use calculation. If you use calculation, you just use cosine rule. So BVA squared will be equal to 20 squared plus 30 squared minus 2 times 20 times 30 cos 30 degrees. So from there you get your BVA. Now, either by measurement or calculation, you will easily get this alpha here, so that we'll be able to get the direction of our relative velocity. Once you have gotten that one, you keep the record. You've gotten BVA to be 16.15 kilometers per hour. And the angle between this place and this place, we got, no, sorry, and the angle between this place and this place, we got half is equal to 111.74 degrees. So if from this we really know the direction of this one, and what does that mean? It means that it is like this. You need to add that 20 degrees to it. So it will be 131.74 in this direction. So it will be like this. So please, I am trying to show you this thing so that there is no magic in it. So you will see. So this place will be 360 minus this angle here. So this place is from here to here now will be this one plus 20 degrees. Once you have gotten that, you will now extrapolate this on this diagram about the paths, about the bearing. So you now bring this one to the place of the bearing. So now we are projecting the relative velocity on the diagram of the bearing. So this is from here to here now. This place is 60. This place is 60 degrees. So all this place here is 120 degrees. And this one, we discover that from here to here, from here to this place is 131.74. So it means it came down like this. Please, I want you to follow. So from here to here is 131.74. I have explained to you. In the relative velocity, from the relative velocity diagram, we got this direction. But when we want to extrapolate it here, we have to add this 20 degrees here, because it is between the relative velocity and the 20 degrees that this angle is. So from here to here, it should be 20, this 20 degrees that is between the vertical and the 20 here. We have to add it to the 117. So that's how we got that 131.74. So the angle between the path and the relative velocity, angle between the bearing and relative velocity is equal to 131.74 minus 120, which is equal to 11.74 degrees. That is it. Once you can get that angle, we are done. So that is 11.74 degrees. Once you have gotten this, all other calculations you need to do, you get it from here. That's all you need. Then we were asked the closest distance apart and the time. Fine. The closest distance apart, you draw this one down. You will now draw a perpendicular line from this place to make a perpendicular on this place. You can use your protractor, your set square, your whatever. So it will be here. Then you can say, okay, curve from here, and then I believe you know what I'm doing. Using compass, you just draw and it will form right angle there. So the distance from this place to this place by your calculation or by your measurement is the shortest distance apart. Shortest distance apart. Now, to calculate the time that they came closest together, you measure from this place to this place, because this is the path of the relative velocity. This is the path of the relative velocity. You measure from this place to this place, and you divide it by the relative velocity. By the relative velocity. From calculation, we were able to get this. The shortest distance, you can see this is right angle. This place is the hypotenuse now. So this place becomes the opposite. So shortest distance apart is equal to 40 sine 11.74 degrees. So this one gives 8.139 kilometers. So if you use calculation or diagram to scale, you'll get very close answer. Now, to get this place, you will see the projection of the distance on the relative velocity path is this. And that is this distance to this place. So distance, the time to get to this place, to have this shortest distance apart, that's what we are calculating. So the projection of the initial distance apart over relative velocity is equal to time to get closest. Is equal to time to get closest. And how do we get this? Is equal to AB cos theta, and that will be 40 cos 11.74. And what is the relative velocity? The relative velocity is 16.15. So we're able to get that one now. So we have 2.425 hours. That's the time to get closest. So you can see, once you can draw your diagram, you get it. And even if you can't draw to scale, you can use your calculation and get everything out fast. Another way you can do this is to use vector analysis, totally vector. And when I want to use vector analysis, I can do it either by resolving the vectors along the bearing line, or I use the normal xy axis. So when I resolve it along the path or the bearing between A and B, AB will become my x-axis or the I side, and another vertical component from it will be projected, and I have my own x along this place and y along the perpendicular to this line. So, or I resolve it, I leave it as it is and resolve. So let's try to see how it will look like if I resolve it along the bearing AB. So you can see, we can resolve the velocity along the path AB. I mean anyone, once you know the path. That is along the and perpendicular to AB. where AB will serve as the x-axis and an axis perpendicular to AB serves as y-axis, or along our normal x and y-axis. In either case, we can look at actual paths or movement of the bodies, or consider the relative velocity paths. This is applicable for closest distance apart or time of interception. So, for our normal distance, the knowledge you need now again is differentiation, because that's the only thing you need again along the line. So let's start. It is good you also learn all these techniques, because you might be compelled to use a particular form to solve a problem. Now you can see we have 60 degrees here. The angle between this one and this one is 50 degrees now. The angle between this one and this place now, you can see we have 60 here. So this place is 80 degrees. Now, let us make it plain like this, so it will be easy to view. We have 40 kilometers. We have sorry, this is 60 degrees. So this place is 100 degrees, please. So we have it like this. So let's start from A here. A is 30, 50 degrees. And now, so this one is 100 degrees. So which means it is going to be like this. So this is 90. So this place is 10 degrees. So we can see from here, we can easily work it out. I like resolving along the plane a lot. We can easily work it out. Now let's start. Original position of A when t equals to 0. A is 30 sine cos 50 plus 30 sine, and original position is 0. Position for B. What's B here? It is 40 plus 20 cos. So this place will be 80 degrees. So cos 80. Sorry, initial position of B is 40I 0J. Velocity of B. Velocity of B is equal to 20 cos 80I plus 20 sine 80J. So after time t, the position of A. Now let's check what is the relative velocity. The relative velocity will be VB minus VA, which is 30 cos 50 minus 20 cos 80 I plus 20 sine 50. 30 sine 50 minus 20 sine 80 J. Let me work that out. And as we see from the diagram, the time to get to minimum distance apart is equal to projection of AB on relative velocity vector. Projection of AB on relative velocity vector over relative velocity. So that's why I say you need to have standard knowledge of handling vectors. You know, from that diagram before, we did something like this. So the projection is what we are going to get now. That is this distance. That is the projection of AB on relative velocity vector. Then we will now divide again by the relative velocity. And you will see how we are going to do it in a very simple way. We are using dot products. We are using dot products to handle this now. So to get projection of AB on relative velocity vector, what we are going to do is to multiply this AB dot unit vector along the relative velocity path, and that will be, okay, let me put it like this, unit vector along relative velocity path. That is the projection over, that's the dot product, over relative velocity. And the unit vector of this one is going to be this vector over the magnitude. So let me work it out. This one is 40 here now. So T will be equal to 40I into minus 15.81I minus 3.285. That is so this is the unit vector now, over 15.81, that is the magnitude, plus 3.285 all squared, square roots. Relative velocity now. So you now divide it with the relative velocity. And what is relative velocity? The relative velocity is also equal to root of 15.81 squared plus 3.285 squared. So you can see, so T is actually AB dot relative velocity over relative velocity all squared. So you can see it's fun, just like that. It's fun. So what do we have here now? You know, when it's dot product, you can only multiply this one and this one to get value. This one and this one will give us 0 because ij. So we are going to have 40 times 15.81 over, you know, this one is squared now, this one and this one. So we are going to have 15.81 squared plus 3.285 squared. Very interesting. So you can see the time to get to the minimum distance apart. You have gotten it. Very easy now. So to get the minimum distance apart, to get the actual value of minimum distance apart, is going to be this distance plus relative velocity times the time. So closest distance apart will be equal to this 40, that is the distance apart, 40 minus SB minus SA, SB minus SA initial at time TO plus relative velocity times time. So, and that will give us 40I plus 15.81 times this time. Please, I will put it there. And this is minus 3.2855 G. Let me work it out, please. So you can do that one. So after working it out, I got 1.677I minus 7.963 J. So minimum distance apart is going to be the square of this, the square root of the sum of the square of this. So look at it. And that is the minimum distance apart. Another way you can do that is by doing vector products. Vector products of the initial distance and the unit vector of the relative velocity, or distance apart cross unit vector of relative velocity. Now, to get the distance, we do the cross products. Now, like we said, it will be the projection of the distance, the initial distance, that is relative distance, on the perpendicular of the relative velocity. And let's do it now. Now, so I am doing the cross product of the relative distance and the relative velocity. So it's going to give me 40 times 3.285 over root of 15.81 squared minus 3.285 squared. So that gives me, so I'll do the cross products. So this one is minus 40 because this one multiplies this one. This one cross this one is 0. So that is the answer. So you can see it gives us the same answer either way. Now let's look at another way of handling it. Now I am still talking about along the axis of the bearing. Let's try to see what will it be if we analyze it by the actual motion of the bodies. A at time t equals 0, at time t equals 0, position is xa, and that is 0I 0 cap j. At time t equals 0 is equal to 40I. So you can see now velocity of A, it has constant velocity, is 30 cos 50I plus 30 sine 50. Okay. Velocity of B is 20 cos 80I plus 20 sine 80J. So after a certain time, let's say time t, position of A, position of A is equal to, let's say PA, will be equal to 0I plus 30 cos 30t cos 50. Let's put those ones in brackets. Plus 0j plus 30 sine 50 j. Position of B will be 40I plus 20t cos 80. Let's put down a bracket, please. Plus 20t sine 80. Now, distance PB minus PA, that is the distance between the two of them. Distance AB is equal to, so let's subtract this B from A from B. So that will be 40 plus 20t cos 80 minus 30t cos 50. Alright. For this one, plus 20 sine 80 minus 30t sine 50. Now, this is what it gives me. 40 minus 15.81 t I minus 30 minus 3.285 t j. So actual distance d squared, as in the magnitude of the distance, is going to give me 40 minus 15.81 t squared minus 3.2 no plus 3.285 squared. That is the magnitude of their distance apart at every time t. Now, for minimum distance apart, minimum distance apart, the d dt will be equal to 0. Now, let's find the d dt. So, we have 2d the d dt will be equal to 2 into minus 15.81 into 40 minus 15.81 t plus 2. I think this one was minus, yeah, into minus 3.285 squared n t. So this one will give us 0 at minimum distance apart. I have 0 equals to minus 15.81 into 40 into 40 minus 15.81 t minus 3.2, okay, plus minus 3.285. So this one is going to give me plus 3.285 squared into t. Now let me get this one out. So you can see, after expanding, I got minus 632.4 plus 260.35 t equals 0. So t at the end of the day gave me 2.429 hours. Now let me find the minimum distance apart. And how do I do that? I just substitute this t into this equation here, and that will give me, because this is the time for minimum distance apart. For minimum distance apart. So that calculation is straightforward. Now, I substituted this t inside this equation. So for my minimum distance apart, this is it. And you can see what I got, 8.138 meters. So that is if you make all the velocity along the plane, along the path, the bearing, as in your axis, x-axis. Now let us see when we use the normal, our natural x and y axis, and leave it as it was represented in the question. Let's see how it will look like. Now let's leave it like this. So this place is 30 and this place is 40. So our A, original position of A, XA is equal to, let's make it 0i, 0j. XB 40, this is 40 cos 30, 40 sin 30. So XB minus XA is still the same thing now, since this place is 0, 0. 40 cos 30i plus 40 sin 30j. So this will give me 20 root 3 I plus 20j. Now let's look at the velocity. VA, that is 30. So 30 cos 80 plus 30 sin 8. VB is going to be 20. So all this place is minus 20 cos 70 plus going on 20 sin 70j. Now let's see the relative velocity. VB minus VA. Let me work that one out straight with the calculator. So shortest distance apart, like we did, is going to be this one cross the unit vector of this one. You can see cross this will be the cross. When you cross this one on this, so this is what it's going to give you. So it's going to be, so shortest distance is equal to XB cross VB over magnitude of VB minus VA. So let me represent it as we'll see it. So it's going to be BXA cross BVA over magnitude of BVA. So this is the unit product. See, this is the unit vector. That's the unit vector. So what is our BVA? That's 20 root 3 I plus 20 J cross minus 12.05 minus 12.05 I minus 10.75 J over 12.05 squared plus 10.75 squared. So that will give us the shortest distance apart. So you can see. So when I cross multiply this, it gave me this. And then divided by the square root, I was able to get it. Another way we can get it is by finding the projection of the distance on the relative velocity. And after doing that, we will now divide by the relative velocity, because this is the actual distance traveled. And then, to find it, that's to find the time. But to find this minimum, after getting the time, we will now be able to get the shortest distance apart. So let's first of all calculate the projection of this on the unit vector. So time of what's it called? Time of getting to minimum distance apart will be equal to dxa dot, you can see, is dot dva, that is the unit vector. This is the unit vector. So once we have gotten this, we will now divide again by the velocity. So we are still dividing again by this velocity. So that will give us 20 root 3I plus 20j. So this time is going to be dot product 12.05I minus 10.75j over the square. So it's going to be 12.05 squared plus minus 10.75 squared. So I put it up here again. So it gives 632.42 over 260.77. That's 2.425 hours. Now, the shortest distance will be equal to the initial distance apart plus relative velocity times time. That is the distance at every point in time. So let me put this. Yes. So for the shortest distance, it's going to be this. And what is our initial distance? That is 20 root 3I plus 20j plus minus 12.05 times this time, please, minus 10.75 tji. So let's see what it will give. So look at this. So this is what I got, 5.4174 I minus 6.071 j. And let me find the real value now, the absolute value or the magnitude. So it's going to be root of 66.21. So that gives me 8.137 approximately. So you can see we can use either way. Now you can see. Let's now see if we want to analyze actual motion. That is, we want to do it as in, we don't want to use relative velocity. And you see that it will be proven that this is the same thing. Let's see, what is our initial position for A? We said it's O. For B, we said it was 40, yeah, 40 cos 30i plus 40 sin 30j. So, velocity of A. Velocity of A. We said that was 30 cos 80i plus 30 sin 80j. So, velocity of B, we said that one to be minus 20 cos 70i plus 20 sin 70j. So, which means that position of position of A, position of A at time t, at any time t, is going to be initial position A at t0 plus VAT, and so AA is 0 at t equals to 0. So PA will give us 30 cos 80 t I plus 30 sin 80, no, it should be 30 t, sorry please, j. That's what it should be. So for V, it's going to be initial position of B plus VBT. And what does that give? 40 cos 30 minus 20t cos 70 I plus 40 sin 30 plus 20t sin 70 j. So that is position of B after time t. Now let's get it. This is PA, position of A after time t. This is t. Position of B after time t is BT. That is initial plus the velocity times time. So this is what we got. So after analyzing using the calculator, this is what we got. So distance apart after time t is going to be PB minus PA, and that is, this is what it is. So let's call this to be equal to D. Let's call it D. Now D, the magnitude of D squared, will be equal to this one plus 20 minus 10.75t all squared. That is our D. And we have established that at minimum distance apart, the D, the T should be 0. Let's work that one. Now, this is differentiated, and the D, the T is made to be 0. So this is what it gives. And at the end of the day, we got this. So T is 2.4253 hours. So that gives us, so for us to now find the minimum distance, so this is at t equals minimum. So now to find the minimum distance, you have to bring this one back into this equation here. So let's quickly do that. Now, it is substituted back into this equation. So look at what it gives. At the end of the day, I was able to get this, and d, that is the d minimum is equal to square root of 66.2041, and that is the d minimum. Two ships A and B are 4 kilometers apart. A is due west of B. If A moves with a uniform velocity of 8 kilometers per hour due east, and B moves with a minimum velocity of 6 kilometers per hour due south, calculate the magnitude of the velocity of A relative to B. 2. Closest distance apart of A and B. Now we are told that A is west of B and they are 4 kilometers apart. I was also told that A moves with uniform velocity of 8 kilometers per hour due east, and B moves with uniform velocity of 6 kilometers per hour due west. So this is how A moves. So A moves with, let me see, 8 kilometers per hour. B moves with 6 kilometers per hour due south. So, with what we have done, this one is a straightforward thing. We have this one for, let's quickly do something. Calculate the relative velocity between the two of them. So, this one, it goes like this. Let's make this one stagnant. So, let's make this one stagnant. So, it will be, B will go like this, and then we move in the opposite to make it stagnant relative to A. So, we have this as our relative velocity. So this one is 8, this one is 6. So what is our relative velocity now? Our relative velocity is going to be root of 8 squared plus 6 squared, and that is 10. That's our relative velocity. So what is this place now? We know what this place is. So theta. So we have sine theta is equal to 6 over 10. We have gotten our relative velocity, the direction of relative velocity, and the sign. So what do we do next? We come to the actual path A, B. We will now place the relative velocity motion. We plot it, just like we've said before. And this one will now be this theta. Don't need to work it out. Then the shortest distance, we said it will be this one to this place. And we are told this one is 4. This is the shortest distance. That is the shortest distance. Straight away we get it. So ds over 4. You can see this is the hypotenuse because this is the right angle now. Is equal to sine theta. And what is our sine theta? Which is equal to 6 over 10. Quick one. So ds, the shortest distance is going to be 6 times 4 over 10, which is 24 over 10, 2.4 kilometers. Fast. Explanation just makes it long, but once you've gotten it, it becomes game.